Alright, so we're starting with acid-base balance now. Starting with page 5 of the notes. Acid-base balance basically is exactly what the name says. In fact, I like this little picture here that usually if we're in the class, and this is bigger up on the screen, y'all can see it without me having to make it bigger, but anyway. It really works like a seesaw. And we have a narrow range of acceptable pH for our blood, which is listed in your notes right here. And so the acidic portions and the alkaline portions are our hemostasis maintains a balance between those two. If one starts to go up higher than the other, then there are body systems that will compensate for that and attempt to even this seesaw back out. I always picture it like, driving your car down the road and you're trying to keep it between the two lanes. And then if you start to veer in one direction, you have to correct and come back. If you overcorrect, then you end up in the other lane. So it has to be the correct amount of change. So that's the same way it works with the acidity and the alkalinity. If we start becoming alkaline, the body will compensate and try to pull us back to the middle. But then we have to also watch and make sure it doesn't overcompensate and then it actually becomes acidic. So that's part of just the concept of what that is and what it's doing. It's the balance between those two entities to try to keep us between 7.35 and 7.45 pH of our blood system. Okay, and then when we talk about some of these terms, hopefully you remember the previous part when we talked about the main 4 electrolytes, sodium, potassium, chloride, and CO2, we said that CO2 in the lab is usually measured as bicarbonate. That is because CO2 is a gas. Analytes can usually get measured as like milligrams per deciliter or whatever. And we did talk about already with enzymes, that enzymes are different. They're measured in activity units. So gases are different also. Gases are not measured in milligrams per deciliter. They are measured as partial pressure. That's kind of like a flashback to high school physical science there and Avogadro's law and all that stuff. But gases, are just like inflating your tires in your car. It's partial pressure. So it didn't get put in this part of the notes, but I usually go over this here. When we talk about some of these terms, and you see them listed here as like PCO2, usually there's like a PO2 somewhere. PO2, that is the partial pressure. The P is the part. So it's the amount of that gas, but it's simply the units that we're measuring it in. So the partial pressure is how we're measuring that gas. So we have some little vocab words here in case they get used in a question, just so you're familiar with them. Hypercapnia, increased amount of CO2 in the blood. Remember the P is just the partial pressure. So increased amount of CO2 in the blood. Hypo is decreased amount. Simple enough. We just talked about this balancing act over here. That's what this part's referring to. Anything that's throwing this balancing act off could be considered an acid-base disorder. But how it's throwing it off is where it comes down to single versus mixed. Simple acid-base disorders result from a single primary disturbance. The person is having trouble breathing. Their kidneys are failing. Whatever that one root cause is, it's throwing the balance off. So that's a simple disorder. Mixed is the patient has a little bit more problems going on. And so mixed, maybe I'm having trouble breathing, and instead of maybe it's I'm having trouble breathing and my kidneys are failing. So mixed, there's more than one thing going on. And what's interesting about the mixed disorders is if I have 2 disorders going on and they're both going to cause acidemia, then I'm going to have some very serious acidemia going on. And then same thing if I have 2 different disorders going on and they're both going to cause alkalemic states, then I'm going to have some really serious alkalemia going on. However, if my mixed disorder is one disorder that's going to cause acidemia and a different disorder that's going to cause alkalemia, I still have all the problems that those disorders are causing, but my pH may actually stay within or very close to the normal range because they're both working against each other. So the mixed disorders can be very confusing. It is difficult for the BOC to ask you an in-depth question about the mixed disorders. What they tend to do, because you're really getting into pretty in-depth diagnosis at that point, so what they tend to do, if they're going to ask you a question about the mixed disorders, it usually tends to be you recognizing that the patient situation that's being explained to you is not explained by, say, choice A, kidney failure. It's not all explained by choice B, difficulty breathing. It's not all explained by choice C, whatever choice C is. And then choice D may say that it's a mixed disorder. You're more picking that when it's the appropriate choice. You are not usually diagnosing to the point of saying, oh, this patient has blah, 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 and blah, blah, blah. It's more recognizing, could their problems have been caused by one cause, or is there more than one thing going on? Okay, compensation, the body's response to being out of balance. If the body did not compensate, then our question and answer things on these kind of would be much easier. But that's just not what happens. What I mean by that is when if the kidneys are failing, if the body did not compensate for that, then we would have very clear-cut lab results, and we'd be able to tell, oh, look, the kidneys are failing. That's what's causing this acid-base disorder. But that's not how life works. If the kidneys are failing, then the lungs try to change their behavior in order to compensate for it. So it makes the lab work sometimes not quite as clear-cut. Again, looking at this from a VOC point of view, because that's, maybe for a lot of this is what we're looking at, is to understand this enough to be able to answer those style of questions. The way they figure in compensation into these questions is usually saying, like, if the patient is in metabolic acidosis, why is the pH almost normal? Because, the answer would be because the body is compensating. Or what the favorite way they have of asking compensation questions is usually the patient is in metabolic acidosis due to blah blah. Which of the following would be the patient's compensation for this? And then you're picking how the body would respond. We're going to go over this stuff, but it's just to make sure that you understand what this term is and what we're talking about. So compensation is not the disorder. Compensation is the body's natural response to trying to fix this disorder. All right, so when we talk about acid-base balance, it is more in-depth than these two terms that are listed here for you. But to interpret them, this is really the easiest way to look at it. We look at it as bicarb being the base. Bicarb levels are controlled by your kidneys. Kidneys can choose to either retain or increase the amount of bicarb in the body. So bicarb begins with B, so we can remember that bicarb is the base. CO2 is the gas, of course. It's considered to be the acid. And so the lungs, because that's our breathing. The lungs can either increase or decrease the amount of CO2. So if I am in a state if I have a disorder that's causing me a state where my pH is now at base, then I'm going to try to retain acid to lower my pH. If I am in a state that's causing my pH to be acidic, then my kidneys are going to try to retain the base to try to bring my pH back up. So again, it's all a balancing act. As this seesaw dips in one direction, this other side tries to pull it back to where it belongs. All right. So there are multiple buffer systems in the body. They're listed here for you. But the main one that plays in the acid-base balance within the chemistry environment is this top one that's highlighted for you. Bicarbonate and carbonic acid. Uses bicarb and carbonic acid to minimize pH changes in plasma and RBCs. It is the most important buffer system of plasma. So when we're talking about acid-base balance, it is usually related to the bicarbonate carbonic acid. And that also goes for VOC as well. But just to know, there are other buffer systems. Protein uses plasma proteins to try to minimize pH changes. Phosphate takes you between hydrogen phosphate and dihydrogen phosphate, and then hemoglobin. Uses hemoglobin in the red blood cells to minimize pH changes in the blood. So when we talk about acid-base, we're really, for chemistry, we're talking about the bicarb carbonic acid. And again, remember, bicarb is your base, carbonic acid is your acid. We simplify that and look at it as being CO2. CO2 is really part of this carbonic acid. If you look at it, CO2, see how you have an H2O left over? It's really CO2 plus a water. So CO2 plus a water becomes this carbonic acid, and that's why we think of carbon dioxide as our acid. Because if we look at it as carbonic acid, it can confuse the problem that we're trying to answer. But if we look at it as carbon dioxide, we can remember lungs monitor the carbon dioxide levels. And this is not a creation of mine. This is also how reference books present it to you. That it's a choice between bicarb and carbon dioxide. But when you get down into the actual names within this system, then technically it's carbonic acid, which is CO2 plus water. Okay, a little refresher of the main circulatory system. Blood passes through the lungs. While in the lungs, oxygen moves into the blood and CO2 is removed from the blood. The reason that we go back over this background is thinking about if we are going to say that the lungs are going to compensate for something by speeding up breathing, then we want to think about what's happening when we speed up breathing. Well, if CO2 is removed from the blood, then when we speed up when we speed up breathing, then we're increasing the amount of CO2 that we can remove from the blood. So if we are removing increased amounts of CO2, then we are removing amounts of the acid. If we say that the body is doing something by slowing down breathing, then if we slow down breathing, we're slowing down how much CO2 is removed from the blood. So in that case, we're trying to retain the acid. That's how we look at these body systems and their effects. So when we say lungs can retain or increase excretion, it would retain by slowing down breathing. It would increase that excretion by speeding up breathing. Okay, and then arterial blood gases, obviously from the name, requires an arterial blood sample. The arterial blood gas, I said in the lab we don't measure gases. We tend to measure bicarbonate when we're doing our electrolyte panel. Arterial blood gases actually does measure the partial pressure of the gases. So that is the methodology in which you can actually get a direct CO2 measurement. So an arterial blood gas usually will measure the pH, the oxygen, and the CO2. In fact, it technically is measuring the PO2 and the PCO2, the partial pressure of each of those. Sometimes the BOC will ask a random question about an arterial blood gas. So please, it's not highlighted here. I don't know why it's not highlighted here. I was thinking that I think that we maybe had a test question on this one, so this really should be highlighted. But whether it is or not, I still need you to know that arterial blood gases are drawn in heparinized syringes, and the specimen has to be transported in cracked ice. Now, what's cool about this is cracked ice. I wonder if it's going to pull up a decent picture or not. Let's see. No. What about if we look up sonic ice? Yeah, this is what cracked ice is. Cracked ice, it means these little bitty fragments of ice, right? Sonic ice is the best ice. Compared to cubes. If you put a syringe of blood into cracked ice, because it's so much smaller of ice, the ice will be able to condense and surround that syringe and cool the syringe the same all over. That's considered to be homogeneous, right? Homogeneous cooling. Whereas if you put it in cubes of ice, there's more airspace left between the ice and the syringe because the cubes can't close in around the syringe as well. So then the syringe will not be cooled as evenly throughout. So cracked ice is considered to be the acceptable transport for the heparinized syringe for blood gases. So please know that. Okay. back on topic now with that. What? I'm skipping all of. Is this just questions over here? Yeah, this is just questions. So we'll get to this. I might just do a separate one with this because I'm gonna get tired. So let's just make this bigger, and I'll probably come back to the PowerPoint in a separate recording. So acid base that we're talking about here is basically these two components: the lungs and the kidneys. Hang on, I'll take a sip of water. As a patient, if I have a disorder that is affecting my lungs, then I'm going to be in a respiratory condition. This respiratory condition can cause my pH to become acidic, and then I would be in respiratory acidosis. Or the lung condition could cause my pH to become alkaline, and then I would be in respiratory alkalosis. That's how those two things are differentiated between. So respiratory acidosis and respiratory alkalosis simply means that it's the lungs usually causing a problem. So if breathing is inadequate, CO2 builds up and ends up forming carbonic acid, and there'll be an acidic pH. So when it says breathing is inadequate, in a test question, that could be the patient has asthma, the patient has emphysema, the patient, I'm blanking now, but any other condition that's going to cause hypoventilation. Hypo meaning low, right? Hypoventilation. Pneumonia. Patient can have pneumonia. Patient can have cystic fibrosis. Breathing is inadequate. So if they are not doing an efficient oxygen exchange, CO2 is going to build up, and that could be causing the acidosis. Now, if the opposite is true, if they're hyperventilating, if they are what else causes breathing fast? Panicking, I know there's probably syndromes that cause hyperventilation, but anyway, then you're expelling too much CO2, then you're going to be in respiratory alkalosis. So we're going to talk about these, but just remember, we're going to look at the pH, and we're going to look at what body system is involved. So if the pH is low, and if it's the lungs, respiratory acidosis. If the pH is high, and it's the lungs, respiratory alkalosis. And then the kidneys are considered to be the main metabolic part. And so, same thing. If the patient's pH is low, but if it's a kidney disorder, you're going to call it metabolic acidosis, and if the pH is high, metabolic alkalosis. So, don't look at this column yet, we're going to get to this. But remember, we categorize the acid-base disorder based on what is causing it. So, in fact, I'm going to come back to this up here. But this is our main way that we go through and classify them. So based on the pH, usually a question will give you a pH. You're going to determine whether it's acidosis or alkalosis. So if it's a 6.8 pH, then you know it's one of these acidosis states. If it's a 9 pH, you know it's one of these alkalosis states. If they give you lab work to look at, then you can start thinking about these columns to categorize it. So if the PCO2 is altering oppositely of the pH, think about what that means. So if the pH is going down and the PCO2 is going up, then think respiratory. And see here how with this other respiratory pH is going up, PCO2 is going down. So in a test question, if the PCO2 is going in the opposite direction of where the pH went, then we're in respiratory. If they give you a bicarb result, and if the bicarb result is going in the same direction as the pH, then think metabolic. This is not the only way to categorize these things. This is one of the ways that textbooks will go through and have you categorize these things. The reason that you may want to look at it this way for some of them is if the test question does not give you patient information. If a test question gives you patient information, such as one of these disorders listed here, usually I start with that. Well, I always start with pH first. So I'll start with pH first so I know if they're alkaline or acidic. And then if the test question tells you the patient has COPD, or if they have Cushing's syndrome, then I'm going to use that to help determine what state they're in. But if the test question does not give you information about their disorder or what's going on with them, if the test question only gives you lab results, then this is a really good way to categorize them. Don't panic it if this part seems complicated to you. I probably have not done a very good job explaining it at all, but that is part of the reason why I'll do a separate recording over here with some examples and some questions, and I think that will help it make a lot more sense to you. So I told you we'd come back up here. When we have categorized what their main disorder is, sometimes we're done with the test question, but sometimes we're not. Sometimes what the test question may be asking you is something about the compensation. So that's what these last two columns are for. If the patient is in a respiratory acidosis, meaning that it's their lungs that are primarily involved, then the kidneys will be what's going to run the compensation. So remember, if the lungs are failing, the kidneys will try to compensate by correcting the pH. And so that's what the bicarb and this explanation here mean. And then same thing, if the primary problem is metabolic, meaning that it's the kidneys that are screwing things up, then the lungs will try to compensate, and this is what they're going to do for their compensation. Okay, we kind of covered this already. Arterial blood gases, I kind of touched upon earlier, but just to have a separate little section of notes on it. Arterial blood gases include a bicarbonate value. If the arterial blood gas, if it reports a bicarb, it's calculating that from the CO2 measurement. The blood gas instrument measures pH and the partial pressure of PCO2, and then you're going to tell you that, and then calculates a bicarb. Utilizes the Henderson-Hasselbalch equation. Now, for this one, I did highlight it correctly, because notice how your highlight ends here. You don't have to memorize this for this test in here. You're not going to work any problems to do with this. This is simply, you may or may not have a question that has you pick out that arterial blood gas instruments use the Henderson-Hasselbalch equation compared to, other equations listed or something. But you're not going to have to work these, and on the BOC, you should not have to work one of these. Okay. So, interfering substances with arterial blood gases. This is important to know. And again, with arterial blood gases, remember we're talking about, this is getting drawn from an artery. Where was that at? It's getting drawn from an artery with the syringe. Where did that go? I know it was here. I'm looking now. Because we talked all about the eyes. Oh, down here, because it wasn't highlighted, and I was only looking at the highlighted things. So remember, when we're talking about arterial blood gases, they're drawing it from an artery using a heparinized syringe. And if the instrument is not right there bedside, if there's going to be transport, then it needs to go in cracked ice. So when we talk about these interfering substances, remember those requirements. So exposure of the sample to air. If room air gets into that syringe, remember gases will travel from where there is more of a gas to where there is less of a gas. That's back in that high school physical science gas law part. If, that is why if I have a helium balloon and I untie it and open up the helium balloon, the helium is immediately going to come out into the room. Not that I'm compressing the balloon and making it come out, but it's going to come out because it's going to go from where there's more helium to where there's less helium. Gases naturally want to spread out and fill whatever container they're in. If the helium's container changes from the balloon to being the room, then it's going to spread out and attempt to spread out in the entire room. That's the same way it's going to work here. So if there is air in the syringe, that air is not going to stay in a pocket. It's going to attempt to spread out throughout that sample, which is going to lower the amount of CO2 that was actually there from the patient's sample. So you're going to have a falsely low PCO2, a falsely high O2 because of the oxygen from the air, and a falsely high pH. Delay between collection and testing. It should be kept on cracked ice. We already talked about why instead of cubes. it needs to be on the ice because just like we talk about with our regular lab work and how whole blood needs to be separated if we're going to be testing plasma because the RBCs and everything stay alive and they keep doing their metabolic processes, it works the same way here. In the syringe, those cells are still alive, so they're going to keep doing glycolysis. When the glycolysis cycle is going on, that's going to lower the pH, lower the PO2, and raise the PCO2. So you want it on ice to slow down glycolysis to minimize the amounts of these changes. If the person drawing the sample got blood from a vein instead of from an artery, remember veins are returning to the heart. They've already delivered their oxygen. So the blood in the sample is going to have a falsely low O2 and a falsely high CO2. I say falsely. It's going to be a true result for that venous blood, but it's going to be falsely these based on what the arterial blood actually would have shown. A non-heparinized syringe could give either falsely high or falsely low results because it's simply the fact that arterial blood gases are standardized based on a heparinized syringe. So if you switch up your anticoagulant, you are now off the manufacturer's directions and your results are just simply not reliable. If the patient has a high white count or a high platelet count, white cells and platelets will use up the extra oxygen from the blood. In fact, I love this little term. It's called leukocyte larceny. And so it will cause your results to not be accurate because, all these things are calibrated and standardized based on a comparable white count and platelet count. If the patient has leukemia and they have a 50,000 white count, or if they have some kind of disorder where they have an extremely high platelet count, then those are using up oxygen from the bloodstream and will alter results. I would guess make a falsely low oxygen. And then Clotson sample causes a non-homogeneous sample. If my sample I drew is in a syringe, and then I run the sample, when it goes into the little point-of-care instrument, it may take half of the sample, or it may take 3/4 of the sample. And then it sucks it in, and then it runs it. Well, if it's a non-homogeneous sample, because there's clots or whatever, the part in the back of the syringe that didn't go into the instrument may be hogging extra oxygen or hogging whatever, and so you no longer have an actual valid result because your sample was not the same throughout. Okay. And then our last topic, and I say that knowing that we're still going to go back to acid-base in the PowerPoint with the examples and stuff, but I just want to finish the notes since we're right here. And osmometry is such a small little topic here. So osmometry is kind of becoming an outdated methodology, but it's still a validated one, so they could potentially have a VOC question to do with it. It reflects the osmotic pressure, so the pressure of water distribution among the body. So just a little refresher here of the definition of osmolality. Probably never thought you'd see that again after your chemistry classes were over in Kirkman Hall, but osmolality, the measure of the solute concentration of a solution. So how many particles are dissolved into that solution. Osmolality does not differentiate of the size of the particles. It doesn't care if they're ions or non-charged. It is simply how much of it. What is the mass? How much of or the number of particles? How many particles are dissolved into the solution? So osmolality, we have a formula here. You're going to memorize this for your exam. You're not going to have to calculate it, but you may have choices to where you're picking which one is correct based on an example, or you may even have a free text box where you're given information and then you're typing this out. Measuring osmolality in this method can help determine if the metabolic acidosis is caused by non-electrolytes, the presence of some of these other substances. The difference between a measured osmolality and a calculated is called the osmol gap. And it represents other osmotically, I can't say that, obviously active substances. What that means, even though I totally mangled that sentence, what that means is where we can measure osmolality in the little instrument. St. Pat's used to have a little instrument. I think they still do. I don't know about the other hospitals. Well, I know Calcam doesn't, but I don't know about Lake Charles Memorial. But so if you're running into the instrument and you get your result, great, you're done. But you can also calculate it and then get the difference between the two. And what the calculation does is, see, the calculation is only considering sodium, blood urea, nitrogen, and glucose. So the difference between this and this represents any of the analytes that are dissolved in the solution that are not one of these three things. So it's the ones that are not in the formula. Kind of like an anion gap. I mean, it's really the same difference. The anion gap that we talked about earlier with electrolytes is trying to see the difference between the measured electrolytes and the unmeasured electrolytes. And it's the same concept here. Okay, and the most common method of doing osmometry is freezing point. I have nothing else to say about that. So I'm going to stop this here, take a little break, and then try to do a better explanation for solving these acid-base problems with the examples that we're going to go over.